Hello everyone. You are watching this video lesson right now because either you are absent from class and this is how you're going to catch up, or we had Wi-Fi issues in the building on Friday, April the 30th, and therefore you need to receive your regular Friday science lesson asynchronously rather than live, okay? So we're going to back up a little bit and remind ourselves what we talked about last class. So last class we learned that heat transfer follows a specific pattern. Just like any other energy can transfer from one place to another. Thermal energy can also transfer from one place to another, from one object to another, from one system to another system. And what we learned is the specific pattern of transfer is from hot to cold. So when two objects meet that are at different temperatures and one object is cooler or lower in thermal energy, for example, the surrounding air in your kitchen, and the other object is warmer because it has more thermal energy, for example, a hot mug of coffee, the thermal energy will always transfer in one particular pattern or direction, and that is from the hotter object to the cooler object. All right, so in this case, heat will transfer out of the hot ceramic mug into the cooler surrounding air. And that is why if you wrap your hands around that coffee mug, your hands feel warm because your hands are cooler compared to the hot ceramic mug, and therefore heat is transferring into your skin and you feel warmer. So we went over all of these. We left off at the cake. I believe block 5 we did this one. But this is the reason, due to heat transfer, this is the reason why you need to wear oven mitts when you take out food from the oven, because your hand is much cooler compared to the hot cake that just baked in the oven. So what we would do is we would show that the heat is transferring out of the hot baking pan into the mitts. And this is why you need to wear the gloves to protect yourself from such a fast rush of intense thermal energy that could cause third-degree burns. So let's take a look at the soda. Remember, I talked about this before. We could go to New York City and randomly just pull 100 people and survey them and say, you want a nice, cool, refreshing glass of soda. What are you going to do to make it cold? And they'll say, put ice in it. And then you ask, well, why does the ice work? What happens when you make a system of soda and ice and put it together? And they'll say it's because the coldness from the ice moves into the soda. That is 100% inaccurate, because heat only can travel from where it's warmer to where it's cooler. The reality is the heat leaves the soda and transfers into the ice. This is why the ice eventually melts, because the ice is gaining thermal energy. So therefore it's increasing in temp, and it gets closer to 0 degrees, then it gets above 0 degrees, and the ice has melted into liquid. So where did that heat come from? It came from the warmer soda. So if the soda is giving up the thermal energy, you're going to notice that the soda temperature drops, and that's how you get cool, refreshing soda. So what we're going to do is we're going to draw, I'm going to do it at the bottom of the glass because it's solid soda down here. And I'm just going to show that heat or thermal energy transfers out of the warmer soda into the cooler ice. Notice I said heat transfers. Heat, remember I taught you this, heat, the true definition of heat is the transfer or movement of thermal energy. So if I say heat transfers, it's okay. It's technically accurate because I'm talking about thermal energy that is leaving one place and going into another. And then we're just going to add, just clarify that the thermal energy leaves the warmer soda and transfers into the cooler ice. So what I'd like you to do on your own is go ahead and complete these two scenarios. So how would you draw heat transfer or energy transfer for these two individual scenarios? For homework, I asked you to do foot therapy, and the plan is that we will review those answers together as a class on Monday or Tuesday, depending on whether I have you A day or B day. So we'll look at it on Monday or Tuesday of next week, the 3rd or 4th of May. Thermal equilibrium. So one of the things that we identified last class is that the warmer object will give off heat, but it will not give off all of its heat. So the warmer object will lose heat and cool down, and the cooler object will actually receive that heat and warm up. But it's not going to be a flip-flop where the cooler object now becomes the warmer object and the warmer object now becomes the cooler object. What happens is they meet at a specific temperature. So for as much thermal energy that the warmer object gives off, that is equal to the amount of thermal energy that the cooler object gains. That specific temperature can be calculated, and it is called thermal equilibrium. So thermal is Latin for heat, and equilibrium obviously means equal or the same. So what you need to understand is that when you have two objects in contact with one another, heat will transfer until thermal equilibrium is reached. At that particular temperature, there is no longer any transfer of thermal energy between the two objects. So that means they are at equal temperatures, which means the molecules of each substance have the same average kinetic energy. Okay, I want you to try number 1 on your own, and again on Monday or Tuesday, we will go over that answer. Number 2. So here we have a system in the middle cup, and it came from 2 individual cups. We do not know what the liquid is. Let's say it's milk. We have warm milk on the left and cold milk on the right. Just as a point of reference, 10 degrees Celsius is basically taking something very cold out of the refrigerator. And 20 degrees Celsius is equal to room temperature, about 70 degrees Fahrenheit. So at the same time, you're going to take the warm milk and the cooler milk, pour both of them into the middle cup. So now this is our new system. And what you want to do is determine after about 10 minutes, because you're giving time for heat transfer to take place, you're giving time for the warmer milk to give up some thermal energy to the cooler milk molecules. So after 10 minutes, there's been plenty of time for the new system in the middle cup to reach thermal equilibrium. And the question is, what is the thermal equilibrium temp? The thermal equilibrium temp cannot be 30 degrees. That's impossible, because basically you're saying that the cup would be warmer than the original warm milk. That's not possible. It cannot be 5 degrees because you're saying that the middle cup system would be colder than the original cold milk. That's not possible. Your D is also not possible because there is no way that the system would be as warm as the original warm milk, because you already know that the warm milk has to give off and transfer some heat to the cooler milk, and that the cooler milk will warm up a bit. So that basically leaves these 2 options. So hopefully at this point, many of you are thinking you would just take the average of 20 degrees and 10 degrees. And that is accurate. So this would be your math work up here. You would take the temperature of the 2 original substances, add them together, and then find the average of that temperature, the combined temperature. So there's 2 objects in the system, so it would be 30 divided by 2, which is 15. So the correct answer would be 15 degrees as your thermal equilibrium temperature. Now, this math is very simple. I'll allow you to always use a calculator, but just remember to calculate or determine thermal equilibrium temperature. You would take the average temperature of the 2 individual systems. Let me show you why that works. So what you're saying is that the warmer cup is 10 degrees warmer than the cooler cup, right? Because 20 minus 10 is 10. So you would take that 10 degree difference. That's called the temperature differential. And it's a fancy way of just saying temperature difference. So if you determine the temperature difference to be 10 degrees, in other words, these two cups are 10 degrees apart from each other, you would take that 10 degrees and cut it in half, which is 5. And basically what you're saying is the warmer cup loses 5 degrees of heat, so 20 minus 5 is 15. There's your thermal equilibrium temp. And the cooler cup gains 5 degrees of heat, and that 10 plus 5 is 15. So again, what I'm doing is I'm showing you two ways mathematically that you can determine thermal equilibrium temp. The quickest way, of course, is to just calculate the average. Okay, go ahead and scroll down to page 12, please. Now on page 12, we have a whole new scenario here. We have a system. This is a big beaker, small beaker system. The big beaker is holding a very cold liquid at 5 degrees Fahrenheit. Usually we associate the color blue with coldness. And then the smaller container, notice that it's sealed, so none of the liquid can actually leak out and mix in with the blue liquid, because if that's the case, you would have purple liquid, right? So the red liquid stays contained, and it's at 70 degrees Fahrenheit, okay? So basically what we have is a substance at a warmer temp that is now in contact with or touching a colder substance. So the first, if you take a look at the scenario, it says you're going to design a graph that models the two liquids reaching thermal equilibrium over a 1-hour time period. You're going to label the X and Y axis. You're going to create a title for your graph, and the two liquids, an important piece of information to note is that the two liquids reach thermal equilibrium specifically at 20 minutes. So you're watching the system for 1 hour or 60 minutes. And at 20 minutes within that 1 hour, something special happens. The warm liquid cools down to thermal equilibrium temperature, and the blue cooler liquid warms up to thermal equilibrium temperature. So we're going to take it in steps. Step 1, they want you to draw a molecular model of each mysterious liquid. Step 2, calculate thermal equilibrium temperature. And step 3, make a graph. Okay? Okay. So hopefully you stop the video before you looked at this answer. And you can see that both of these, the blue liquid is a liquid and the red liquid is a liquid. So both substances are in the same phase or state of matter, but they do possess significant amounts of kinetic energy. So the red liquid has way more kinetic energy than the molecules of blue liquid. And because of that, we've got a liquid molecular model here. We have a liquid molecular model here. But notice how intentionally the molecules are closer together for the blue liquid, and they're further apart for the warmer liquid. And that's because more kinetic energy means that the molecules are faster. That's what the dust trails are showing. The dust trails are longer and you have more of them. And that the spacing between the molecules keeps getting greater and greater. But over here, the spacing is less, and the dust trails are much smaller and shorter to show that the molecules are closer together and they have less kinetic energy. But again, I want to emphasize both are still in the liquid phase. Okay? So then it says to calculate the thermal equilibrium temperature. So that means you have to find the average of 7 and 75. So 70 plus 5 is, sorry, I said that wrong. 70 and 5. So 70 plus 5 is 75. Divide by 2 and you get 37.5. So what we now know is that when you plop this red container into the blue container and you start the timer as soon as the two make contact, 20 minutes later, both substances are at 37.5 degrees. The cooler blue liquid warmed up to 37.5. The warmer red liquid cooled down to 37.5. And again, that took 20 minutes for that to happen. So what we need to decide at this point is what type of graph is best. So if we are watching how the temperature of the blue water, I said water, but the blue liquid, because we don't know what it is. If we are watching the temperature of the blue liquid changing over a 1 hour time period, and we're watching the temperature of the red liquid change over a 1 hour time period, I hope at this point my key words here that I'm saying is, how does the temperature of these two substances change over a 1 hour time period? How does temperature change over time? So it's a change over time graph. When you do a change over time graph, guys, you know it's a line graph. And right away, you should say, well, wait a minute, there should be two lines on this graph, right? You should have a blue line representing the blue liquid, and you should have a red line representing the temperature change of the red liquid, okay? So at this point, we're just going to go to the graph and decide on our scale. So if time is going to be down here on the x-axis, and the unit would be minutes, right? Because we know there are 60 minutes in an hour, and we know that the 20-minute time period is important in this experiment. So most students would say, I would like a scale of 10 or 20 because it's easy to count, but that's not going to work, and let me show you why. If we do a scale of even just fives, right, and make every tick mark 10, 20, 30, 40, which means this would be 50, 45, 50, right? So 10, 20, 30, 40, 50, 60. That means your x-axis is ending here, and you have wasted a little bit over half of the graph. No, I've told you this before. In science class, whenever we create a graph, we want to make the scale as small as possible to zoom in as close as we can. So then a lot of students would say, well, let's try twos. Twos, however, there's not enough grid space for that. So you could do threes. That would be a good interval to do. So like 3, 6, 9, 12, and so forth. And then your temperature would be your y-axis, right? Because we're watching how temperature changes over time. And our coldest temp is 5, our warmest temp is 70. So starting at 0 would make sense, and we would need to go up to about 70 or 75. This is the one where I would say counting by fives is a good idea. Now, we are doing this on Kami, like digitally, so I know that most students prefer to do graphs by hand because it's kind of hard to manipulate the numbers digitally. However, what I did is I took just one text box, and for example, I typed in 0, and then I just hit the space bar a couple of times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 9 times. And then I was able to type in 6 because I remember we're doing intervals of 3. I would recommend this is probably the quickest way. It's not a perfect alignment, and you can also at the end just click and drag and try to align it up a little bit better. And then you're going to do the same thing up here. You're just going to do one text box and hit return, or you can just do, 7 individual text boxes. That's fine too. And then you can line up each number how you want. Don't forget that you need to label the y-axis. Okay. So that is your lesson for today. And the homework would be for you to complete pages 11 all the way down to 14. So if we go back, remember I said to give number 1 a try. Oh, wait, actually back up a little bit. I told you to complete 2 heat transfer diagrams for these last 2 scenarios. Then I want you to scroll down. You should already have foot therapy done. If it's not done, then you need to do it. Then you're going to scroll down to page 11 and do number 1. And then you're going to complete the graph it out. And then remember I said use a blue line for the cooler liquid and a red line for the warmer liquid. And then you're going to scroll down to page 14 and complete the 6 questions. Okay? That is your homework. If you go to the Due Next Class folder for today, you will see that it's the same thing. The only thing that's not on here is those 2 images of the little girl and the older guy. in the water. You do want to also do that. Complete that. Don't worry about this process grade. It's unpublished. You will not see it. I'm just getting that ready for next week. Okay, everyone. So I hope you have a good weekend. And hopefully you did not have to listen to this lesson because the Wi-Fi was working fine at school. And only students who were absent are listening to this video lesson. And hopefully you found this video lesson helpful and you feel like you're caught up. Have a good weekend.